Hello. So I've been given the difficult task to entertain you for the last half an hour. Hope you're not too tired. I'm sure plenty of you want to have a beer, but you will have to listen to me first. So thanks for inviting me. You might be curious to know why AWS is invited at such a workshop. Um, I'm going to answer that question, of course. First, maybe let me introduce myself. So I'm Arthur Petitpierre. I'm French, based out of Paris. I'm an HPC specialist solution architect for AWS. So I cover the EMEA market, and I have our customers all over Europe, Middle East, Africa, to set up HPC in the cloud along with storage-related project, that kind of stuff. I used to do pretty much the same thing back when I was at Atos. I've been at various roles at Bull before and at HPC customers even before that. And I sometimes plays with snowballs on my bike. I was amazed to see that people were aware of snowballs. I've not yet driven a snowmobile, but I would love to. Anyway, it's interesting for me to be to deliver that talk just after the ITER one, because I used to be one of the architects of the iFERC system that was installed in Rokasho in Japan a few years ago. And I've been there several times, so I know a little bit more than usual people about that project. Now, to answer your question about why we are there, you might not know about it, but we have a deeper relationship with the HDF Group than you might have expected. The Kita project that was shown by John this morning, so that picture is not from me, it's probably from you, and it's from your website. One of the deployment of Kita is actually on AWS, and we contributed with AWS credits to the development of that project. And there are many reasons why we are interested in our customer having access to a good file format for their HPC-related workloads. It's because having that kind of format that helps people to share data, interact, and develop research in general is good for us because AWS is a super nice platform to be able to share data among researchers. And again, you might not know about the fact that AWS has a program to help researchers to share their data. So if you're interested by that kind of stuff, I invite you to read that blog post. Pretty long and explain pretty much in detail how we do host scientific data. That specific data set being stored in HDF5 format. It can be accessed with the H5.5D library and also through the REST API. That's 500 terabyte worth of data. And we actually have a pretty large public datasets program where we do offer different projects to host their data on the AWS. So if you feel like you have an interesting data set that you want to share with other researchers, you can apply on our website and say, okay, I have that super interesting data set. I'm sure it's valuable for many people, and it can be hosted for free on AWS. You might wonder why we are doing that. We are interested too. Of course, data has gravity. So if data are already on AWS, it's definitely also the right place to run the compute. So we are not a non-profit organization. We are not doing that just for the sake of helping you guys. That's also, of course, because it means that if the data are there, people might be using AWS to process them, and that's the way we get our living. Let's switch to another part of my talk, which is how to run HPC in the cloud. So you might be curious because you have your super fast system on-prem. Performance has always been the focus. What you can get in the cloud, on the contrary, might not be as fast. But look at the time it takes to install a system on-prem. And look at the time you are waiting for your research in a queue of a system, waiting for resources to be available. One of the things we can provide on AWS, even if that's sometimes slower, and I'm saying in AWS, but that's true in the public cloud in general, is that given our scale, there's no reason to wait in a queue. And I'm even proudly wearing it. There's no queue in the cloud. There are enough resources to serve all your needs. So instead of having a job waiting for days in a queue because your university, your research center has a system that has a finite amount of resources, in the cloud, on the contrary, compared to your needs, we usually have an infinite amount of resources. Of course, it is finite at the end, but it's probably infinite compared to your needs, except maybe a few of us, so one of the metrics for success when running HPC workloads could also be time to results, and not only the time it takes to run a particular simulation. In the cloud, infrastructure is code, which means that you don't have to redo every installation steps manually each time you have to install something. You can write your infrastructure as code. And I'm going to show you an accelerated demo of how to deploy a small cluster on AWS in real time. That would take something like 20 minutes. So let's launch it. Installation of the tool, configuration of the cluster, and then launching the creation of the cluster. It creates everything in the cloud, and at the end, what you get is a management node on which you can log in. Let's stop that mess. Oh, that's okay. And you're on a cluster with a batch scheduler that's ready to be used, and you can redeploy that as many times as you need. And that demo is done with a tool called Parallel Cluster that at its core is nothing more than a wrapper on our templating system called CloudFormation that allows you to define what an infrastructure looks like. Define a Linux system that's going to be a management node, a set of network rules, a set of compute nodes, and deploy everything for you. And what does it look like? It really looks like what you already know about. When you log on a cluster deployed on AWS, it looks exactly the same as what you have in your lab. Or at least it can look like exactly like that. With a management node, potentially a shared file system, be it an NFS file system or a parallel file system like Lustre or GBFS. You can have remote visualization with 3D rendering. You can have long-term storage, and you can connect that to many other systems like analytics systems, map and reduce cluster, Hadoop clusters, deep learning, some of our deep learning services, all this stuff. And you have super fast access to large-scale storage like S3. That's the most marketing slide I have today, probably. We have a huge range of instances being what you usually know as compute nodes, servers, basically. We do have servers with the latest Intel CPU, with the latest AMD CPU. We do have servers with GPU. You might not know that we do have servers with our own CPU. We do design ARM CPUs, and we are going to design more and more ARM CPUs, probably not yet ready for HPC workloads, but that's going to come at some point. So on that kind of platform, you could test libraries like the one you are developing and using on many different architectures, even if you don't have them in your labs. One other thing you might not know about is that we do design our own network. And when I talk to people about HPC in the cloud, usually the first question or the first argument I'm sent is, well, do you have InfiniBand? Or do you have a fast network? We don't have InfiniBand. And we are probably not going to have InfiniBand, nor in the mid-term, nor in the long-term future. We do operate at a scale where we just can't use InfiniBand. Our scale is higher than that, and the security constraints of a multi-tier, multi-tenant infrastructure are just completely preventing us from using that kind of network. We just can't afford. I don't know if you've seen the latest security issue that Intel disclosed sooner this week about a security problem with random memory access, with remote direct memory access directly linked to InfiniBand network. This is the kind of thing that, as a cloud vendor, we can't do that, and we can't afford to do that. So we do operate our own network, but doing that, we still know that we need to develop some specific things for HPC customers. And that's exactly what we targeted with EFA. So EFA, Elastic Fabric Adapter, is our custom attempt to provide a fast, and by fast I mean both high bandwidth and low latency network for our HPC customers. So we've released almost 1 year ago now our first 3 instances, C5N, P3DN, and I3EN, that do have an interface running at 100 gigabit per second and with a latency, so alpha round trip between 2 instances, of roughly 14 microseconds when measured with an MPI ping pong. So that's still almost an order of magnitude more than InfiniBand, but that probably covers the needs from 90, maybe more MPI application, unless you're a super large scale center like, I don't know, UKMet, Météo France, or things like that. The way it is implemented is slightly different from what you might have seen in InfiniBand. We design our own network protocol and datagram protocol, which is called the Scalable, Reliable Datagram Protocol. And the way we build it is that, so the network we are operating is way bigger than the scale of a cluster where you have an InfiniBand factory with, let's say, a few thousand nodes for the large clusters. Our data centers and our networks are way bigger than that. So it comes with complexity, but it comes with some interesting properties at that scale, among which the fact that we can afford to send our packets through multiple routes. And that's the way we design it. We spray our packets over multiple paths, which allows us to have a pretty reliable latency and a pretty efficient way of handling congestion in that network. I've left just for reference a few comparisons between InfiniBand and our own protocol. But just what you have to keep in mind is this is a protocol that allows us to reach latency and bandwidth that are HPC capable despite the size of the network we are using. How does it look like in real life? So we've run some benchmark, of course, and if you are interested, you can run your own benchmark on that interconnect. Here you have the ideal scalability, and at the bottom you have our scalability before we implemented EFA. And here, that's what we got with EFA. If you were to measure exactly the same thing with InfiniBand, And you've seen the scale here. So the test was done from 200 to roughly 1200 cores. And if you were to run exactly the same thing with InfiniBand, you would be somewhere here. So that's not perfect, but that's better than what we used to do. And here was the real world model that we used. That's a Klingon vessel. So we do have a few instances that are able to use that network. The main one is a C5N, so that's our compute instance with a Skylake CPU. We do also have the same types of instances, but with lots of local disks. So interesting if you want to play with a Lustre file system in front of those instances. And they're both capable of being connected through that fabric. So where can you go from there if you consider library development like HDF5 or any other kind of HPC development or HPC simulation? So what if you would like to test HDF5 against a Lustre file system? You may or may not have such file system in your lab. Well, it happens that we released a fully managed service for Lustre back in November last year. And that part is also available as infrastructure as code. So what does it look like to instantiate a Lustre file system on AWS? So you can do that through a graphical interface. That's one option. If you want to do that with code, you would first write a template. That's the simplest possible version of a Lustre file system definition for AWS. So there is some boilerplate where you just define basically the file format. And then you would define a file system. My resource, oh, there's a mistake in that file, but no matter. You would define a file system, and then you say the file system has a Lustre type, so that's going to be a Lustre file system. You specify some parameters for the Lustre configuration, like it's going to be exported under /scratch. You put it some constraint as far as the network is concerned, and then you specify the capacity in gigabytes of the file system. So here that's a definition for a 7.2 terabyte file system that's going to be exported as scratch. And that's just a definition. So what about deployment? So if I would be to deploy that, so I put that in a file called fsxlustre template.json, and I would first validate that my template is correct. And if everything is okay, it will give me that output. And now I can deploy it with our command line. And that's as simple as that. You launch that command, it will give you back that output, which is the ID of the stack that you're going to deploy. And 5 minutes later, well, 5 to 10 minutes later, no matter what the file system size is, because everything is done in parallel, you will end up with a Lustre file system being available that you can mount on any compute node that you would launch on the same network. Ready to be tested, ready for you to do, I don't know, MPI-IO tests on this Lustre file system. What about when you're done with it? What would you do with it? Well, you just destroy it. You delete the stack, and it will destroy all the resources that have been created by the command I initially used. And what's the cost? So the cost for that is 14 cents of a dollar per gigabyte per month. So if I would be to use that file system to run my test for an hour, that would cost me $1.4. That's basically what it is. What else can I do? Well, you could use the cloud to test on different operating systems, like any version of Linux, FreeBSD, Windows, potentially one day Mac OS. You could test on different CPU and GPU architectures. We have NVIDIA GPUs, we have different models of Intel CPUs. We even have ARM 64-bit CPUs. You could test on different file systems. I've shown you how to do that with Lustre, but you could do exactly the same with NFS, with GPFS, and writing a template for GPFS would also something possible. You can make all this build system automatic. So instead of having somewhere to test your full development environment, you could have a test infrastructure that you would deploy just when you want to run the tests and shut down at the end, and not paying for it when it's not used. You could even set it up so that every time a commit is done to the repository, tests are launched, maybe not full tests, maybe not tests at scale, but some regression tests, some smaller scale performance tests, and when they're done, shut down the whole infrastructure. Thank you. Any question?
So how does SRD compare to Rocky for RDMA over the internet? Is the code available?
The code for SRDP is open source. So the kernel part and the userland part of EFA is based on libfabrics. So we do have an in-kernel driver that is hooked on the InfiniBand subsystem, not doing RDMA, which is in fact not mandatory, but that's still hooked on the same kernel space part. And then on the user space, it's in libfabric. Basically, the driver exports an interface that is compatible with libfabric, and we also ensure that on top of that, OpenMPI behaves the right way on that interconnect. We also work with the Intel guys so that Intel MPI works the right way. And for OpenMPI, we are pretty confident that we are doing it the right way because Brian Barrett, who's one of the release maintainer for OpenMPI, is also the architect of EFA.
So let's say I want to test an application with its performances on the parallel file system. I want n nodes with a Lustre. How can I, or am I sure that actually if I want 4 independent nodes, they are really independent, or the virtualization layer of AWS is hiding something? Because the computer is very different.
Yeah, sure. So our virtualization layer is not hiding anything. It exposes you the different NUMA nodes, how the PCI cards are laid out, that kind of stuff. Then, if you want to be sure you have a full system for yourself, it's not complicated. You just have to take the biggest size of an instance in a family. Like if you look at the C5N family, the biggest one is an 18XL. And when you choose an 18XL, you get the full box for you. So there is no noisy neighbor. Then if you take half of a box, so a 9XL, for example, what you would get is a full socket for you. So when you get a full socket, you should not get any noisy neighborhood problem. When it gets more complicated is when you take a quarter of the box, because you end up with alpha sockets, and then you share the L3 cache. So here you can have noisy neighbor. And everything that is at least half the box or the full box, normally you're not getting any noisy neighbor effect. There's one nasty noisy neighbor effect that might happen at alpha box, which is the fact that from a network standpoint, we commit to give you a minimum bandwidth. And on anything that is less than the full box, you might burst at higher than your share. If the other, let's say you're running on half the box, if the other half is not using its its allocated bandwidth, you might go at more than half the bandwidth. And that's super painful for benchmark because you're never sure that you're at what you should get or at more than what you should get. That's good for customers in general, because the worst that can happen is that you get more than what you paid for. But from a benchmark and or reproducibility perspective, that's rather painful. So we do have a what we call a PFR, or request for functionality, to have a switch that would change the way we give away those resources so that you only get your share and not more than that. That takes time to implement it.
Yes, could you please explain me a bit more of the graphic where you compare the EFA performance?
That one.
How, yeah, I suppose represent how well it scales.
Oh, so if we were not getting any penalty from the scale at which we are running, we would be on the ideal line, which would be if I double the size of, if I double the amount of resources I'm running on, it divide the time I'm running at by 2. That's a scalability curve, not a, yeah, I'm not sure I answered your question.
No, it's just because, for example, you are measuring a penalty, the latency.
So that's not a latency measurement, that's just, we run the same problem at 200 and then 400 cores, and that point would be if it would take half the time of running the problem at 400.
In this case, it's a transmission problem.
In this case, it just means that, yeah, definitely latency is not 0, so it does not scale perfectly, and that's exactly what is expected.
Thank you. Any other questions? Thank you. This is the end of our first day.
Thank you.